Hi everyone, my name is Anna Canoe, and today I'm going to be talking about bone structure stress applications for my theory assignment number 11. Today we're going to be covering stress tensors, the principal stress directions, Wolff's Law, the Koch bone stress diagram, and a recap at the end to tie it all together. We're going to be talking about bones in the body, so keep this in mind as we go through our first couple of slides. Let's start off with the stress tensor. Stress is defined as load per unit area. And now take a small cube of material. Since we know stress is defined as load per unit area, we can see the forces, which are the loads, divided by the area gives us our stress components. So, as we can see in the diagram to our left, a small cube of material has three loads acting on it. The normal load, which are the loads perpendicular to the surface, so F11, F21, and F31, and the two shear loads parallel to the surface. In total, these are the three stress components corresponding to the directions. We can see there are 9 stress components overall, as there must be equal forces opposite to each other for stability. The first 3 are the perpendicular stresses, and the last 6 are the shear stresses. Since some components are equal to each other, the total stress components are reduced to 6, symmetric across the matrix as seen to your right. Represented by the symbol sigma, and can be written as a 3 by 3 matrix, as seen to your right, where the diagonal entries are the normal loads and the off-diagonal entries are the shear loads. Moving on, we can now examine the principal stress directions. Stress depends on location and orientation of the cube, but how can we make this easier? Well, we can do this by finding the principal stress directions, which is the orientation of the cube of material that makes all the shear stresses 0, and we're only left with the perpendicular directions or the normal loads. It is always possible to find this kind of orientation by shifting our axis, and it's much easier to do math with, but is now a shifted coordinate system, so it's very important to keep this in mind as you're doing your calculations. As you can see to the diagram to your left, you first start with a 3 by 3 matrix, which is the description of stresses in 3D. You then apply a tensor transformation, which is a rotation of axes, and we're left with our principal stress tensor directions with all the shear stresses equal to 0, and we're left with our normal perpendicular directions across the diagonal. You might be thinking, these look familiar. Yes, they are. The principal stress directions are the eigenvectors of the stress tensors. Linear algebra. We can now talk about Wolff's Law, which is a great way to explain the bones in our body. Wolff's Law contains 3 main components. That, 1, the optimization of strength with respect to weight, so the perfect balance between the strength of the bone and the animal or organism's weight. The alignment of the trabeculae with principal stress directions, where the bones align with the principal stress directions, or the eigenvectors of the stress directions. And 3, the self-regulation of bone structures by cells responding to a mechanical stimulus. If you're interested in this topic, mechanobiology covers this. Well, now the cells aren't taking a class on linear algebra, so how can they recognize the principal directions? Well, principal stress directions are the maximum and minimum of the stress. So the cells are responding to the stress placed on the system. Essentially, the cells are building and breaking bone in order to keep the stress within a certain range that is manageable and tolerable by the body. We can see this in real life. Koch, a very famous scientist, created the Koch bone stress diagram. Koch found these values, as seen on the bone, by applying loads to a bone and calculating them experimentally, and they lined up with the mathematically calculated stress trajectories. So you can see the values computed show the stress trajectories. What does this mean? It has been proposed that the bone aligns with the stress trajectories, which are essentially the principal stress directions, which are the eigenvectors, in order to optimize the stress placed on the body. Eigenvector values. Cool. To recap, we can see a material stress components can be written as a matrix, a 3 by 3 matrix seen on your right. The diagonals are the normal stress components, and the coordinate system can be shifted in order to have the shear stress as 0, making it the principal stress directions. Wolff's law explains how the bone represents the principal stress directions, essentially the eigenvectors, by three main components. 1. The optimization of strength with respect to weight. 2. The alignment of trabeculae with principal stress directions. And 3. Self-regulation of bone structure by cells responding to a mechanical stimulus. After calculating the values experimentally, they correspond to the mathematical calculations of the principal stress directions, or the eigenvector values, which shows linear algebra applications in our body today. Here are some resources, and thank you so much for tuning into my presentation. I hope you learned something cool. Bye!